Let's go over some ice table sample problems. The first problem involves the thermal decomposition of hydrogen sulfide. Hydrogen sulfide gas is in an equilibrium with hydrogen gas and sulfur solid, S2 solid. The equilibrium constant at this temperature is this value. We start off initially at 6 molar H2S at 1400 K, and at equilibrium, what is the final concentration of H2S. We can also get the final concentration of H2. So a couple of key features that you want to look for, buzzwords, is this idea of after chemical equilibrium has been reached. So that's a big thing. That means that you're dealing with non-equilibrium concentrations. And another big clue to this problem that should give you an inkling to use the ice table is the fact that no H2 or S2 is present in the original sample. Normally, if this was at equilibrium, you'd have some of the H2S, some of the hydrogen gas, and some of the sulfur solid. So no H2 and S2, that's a dead ringer that you're going to have to use the ice table. After completion of the ice table, initially you have 6 molar H2S, so that is 6 molar initially, and we're told we have no H2 at the beginning, so that's a 0. We really don't care about the sulfur because that does not go into our equilibrium expression. And so this reaction is going to be shifted towards the product side because you're going to have to make some of this. And the relationship is that this is going to be minus 2x. Okay, notice the minus 2x comes from the fact that 2 moles of H2S react to give you 2 moles of hydrogen gas, so this is going to be plus 2x. Our goal is to find this value x, where x is considered the change. Again, because we have 2 moles, the change is going to be minus 2x here, and because the reaction shifted towards the product side to generate some of this H2 gas, and we have 2 moles that are generated according to the balanced chemical equation, this is going to be plus 2x. So at equilibrium, we would have 6 minus 2x as the concentration of hydrogen sulfide gas, and we would have plus 2x as the concentration of the hydrogen gas. The equilibrium expression is according to the law of mass action, products over reactants, each one raised to their stoichiometric coefficient. We have no concern with the solid because solids don't have a concentration. And so it's going to be H2, the concentration of which is squared, that's coming from this 2 here, the stoichiometric coefficient, over the reactants, hydrogen sulfide gas, H2S, its concentration squared based on the stoichiometric coefficient of 2. So we're going to plug in our equilibrium concentrations because this only works and equals the equilibrium concentration when you have equilibrium concentration. So we're going to plug in 6 minus 2x as the equilibrium concentration of H2S gas, and we're going to plug in 2x as our equilibrium concentration of H2, and we're going to solve for our change in x, and that will give us our final equilibrium concentration.
With our ice table complete and the equilibrium expression in concentration for these gases written, we now can plug in our equilibrium concentrations for these 2 molecules that will sort of settle, and they have to settle for by satisfying this equilibrium constant and equaling the constant of 2.2 times 10 to the minus 4. So we have everything complete. All we have to do now is solve for x, which is our change, and then plug back into that value of x to our equilibrium. So 2.2 times 10 to the minus 4, and this square, I can make it a whole square, so it's going to be 2x divided by 6 minus 2x, and I'll just make that whole squared. And what I can do then is square root both sides of the equation. So by taking the square root of 2.2 times 10 to the minus 4, I take the square root of this, and that actually pops out, and I'll get 2x divided by 6.00 minus 2x. The square root of 2.2 times 10 to the minus 4 is 0.0148, and that has to equal to 2x divided by 6 minus 2x. So I will isolate the x term by multiplying by both sides of the equation by 6 minus 2x. I will distribute this and then isolate my x term. So solving for x, I get the change of x to equal 0.0439. Our equilibrium concentrations now for H2S be 6 minus 2 times 0.0439, and that's going to equal to 5.91 molar. That will be the concentration of H2S. Corresponding concentration of hydrogen gas is going to equal 2 times our change in x, We calculated x to be 0.0439, and that is going to be 0.0, and our concentration of hydrogen gas will be 2 times 0.0439, and that is going to be 0.0878 molar. We can do a double check. We know our equilibrium expression, Kc, is the concentration of H2 squared divided by the concentration of H2S squared. We have already calculated our equilibrium concentrations. So H2S, we calculated it to be 5.91 squared, and H2 at equilibrium, we've calculated it to be 0.0878 squared. Calculated the equilibrium concentrations, we plug it back to the equilibrium expression, and when we do that, we get a value of 2.2 times 10 to the minus 4, which matches the equilibrium concentration that was given in this problem. So they match, you know you have the equilibrium concentrations correct. Second problem, we're being asked to calculate the equilibrium partial pressures of reactants and products reaction at 500 K if the initial pressures are 0.56 atmospheres and 0.50 atmospheres for each of those reactants. So again, look for key words here. One of them is calculate the equilibrium partial pressures. The initial pressures are this and this, so they're going to settle to an equilibrium pressure. Doing that, we will have to figure out the pressure of Cl2 given the pressure of PCl5 and PCl3. Remember that at an equilibrium, you're going to have some reactants and some products. So let's start off with our ice table. The initial pressures for PCl5 are 0.560, and the initial pressure for PCl3 is 0.500. Cl2 is 0. Change, now in an equilibrium you're going to have to make some Cl2, so the change is going to be minus x, plus x, and plus x. And at equilibrium you will have change of 0.560 minus x as the reaction goes from left to right. Products are going to increase with this increment x in terms of PCl3, and Cl2, whose equilibrium pressure that we are interested in, will be x. Since we're given pressures, we'll call it Kp. It's going to be the pressure of Cl2 times the pressure of PCl3, that product divided by the pressure of PCl5. This is the law of mass action. Plug in our equilibrium expression, pressures. Our equilibrium pressure at PCl2 is going to be x. Equilibrium expression of PCl3 is going to be 0.500 plus x. Equilibrium pressure of PCl5, the reactant, is 0.560 minus x. All of that has to equal to Kp. The Kp at this problem is 23.6. So we have to do a significant amount of algebra here in order to isolate the x term. So I will distribute this x in the numerator and get 0.5x plus x squared. That has to equal to 23.6 times 0.560 minus x. And so let's distribute this and see what we get. 5x plus x squared. When I distribute this, I'm going to get 13.22. 23.6 times 0.560 is that value, minus 23.6x. And now I'll put all my x terms one side. Get x squared is 23.6x plus 0.5x minus 13.22. That's going to equal to 0. I have a common x term here. I will do 23.6 plus 0.5, 24.1. So x squared is 24.1x minus 13.22 is 0. So this is in the form of a quadratic, so we'll use the quadratic equation, which is minus b plus or minus the square root of minus 4ac over 2a. Minus b here is minus 24.1, so minus the square root of this thing, b squared minus 4ac is also known as the quadrant. Squared, 24.1 squared, and 24.1 squared on my calculator, I get 580.81. This 4a, my a value is 1, c value is minus 13.22. Okay, don't forget this value of c is not 13.22, it is minus 13.22, so you need to add the minus there. All of that divided by 2a, my a term is 1. Oh, I will calculate the quadrant here. Term underneath the square root. This becomes 580.81 plus 4 times 13.22. This term is underneath the square root is going to be the square root of 633.69. Take the square root of that. 25.17, so I have 24.1 plus minus 25.17, carrying an extra digit there, divided by 2. I have two values here. I have minus 24.1 minus 25.17 divided by 2. Value is meaningless. That will give you a negative value of x. You cannot have a negative value of x because there's no such thing as a negative pressure. A negative value of x, this x value cannot be negative, or the equilibrium pressure. So we omit the value, we just simply throw it off. We'll go with their value, minus 24.1 plus 25.17 divided by 2. And doing that on my calculator, that is your change. My value of x here, I can plug it into my equilibrium expression. So my equilibrium pressures are now going to be, the equilibrium pressure of Cl2 is just going to be x. We calculated x as 37. Equilibrium pressure of chlorine is 0.537 atmospheres. Equilibrium pressure of PCl3 would be 0.500 plus 0.537, about 1.7 atmospheres, or 37 atmospheres, excuse me. The equilibrium pressure Cl5 equal to 0.560 minus my change, calculated for x, calculated as 0.537. 560 minus 0.537, that will yield me a value of 0.023 atmospheres. Say 0.0234 atmospheres. So there are equilibrium pressures. We have reactants and products at the end of the reaction. We can check our values to see if they are kosher. The way we can do that is by plugging in these equilibrium values back to the equilibrium expression. So let's do that here. We know our Kp from the problem is 23.6. Was given to us in the problem. Equilibrium pressure Cl2 that we calculated was 0.537. Equilibrium pressure of PCl3 we calculated as 1.037. Equilibrium pressure of PCl5 we calculated that as 0.0234. And this, or no, putting that in my calculator, I find that a value of 23.79 equilibrium expression that given to us in the problem is 23.6. That is good enough for it to equal. I'm very confident that the pressures that we calculated were indeed equilibrium pressures at the initial pressure of 0.560 PCl5 and 0.50 for PCl3. So notice you start with this and you end with a little bit of less of PCl5 and a little bit more of PCl3 because the reaction has shifted towards the right, towards the product side. Part B is an application of Le Chatelier's principle. If more chlorine is added to the equilibrium, or if more chlorine is added after the equilibrium is reached, that's a very important distinction. The reaction has achieved equilibrium, the steady state of products and reactants of these gases. If you perturb it by adding more chlorine, so the addition of more chlorine is actually adding something to an equilibrium, and the equilibrium will offset that change. So we would expect a shift left, reactant side. Means your pressure of Cl, the pressure of Cl2 is going to decrease, the pressure of Cl3 is going to decrease, and then finally what will increase is the pressure of PCl5. Addition of chlorine will shift the equilibrium to this will decrease, and that will increase. This is an offset of the perturbation of the equilibrium, and it conforms to Le Chatelier's principle. A problem that involves the ice table involves this reaction, and so if the equilibrium constant Kc is 5.1 at 700 K, calculate the equilibrium concentration of the four gases at 700 Kelvin if the initial concentrations of each of them is 0.050 molar. So gases, this time we're being asked to calculate where the equilibrium will shift, and we're given them in terms of concentrations. Remember in the previous problem we were given the gases in terms of pressures. So let's first calculate not K Kc, but Qc for this because we want to know where the equilibrium is going to shift. Is it going to shift to the left or is it going to shift to the right? So Qc here is the concentration of CO2 gas times the concentration of H2 gas divided by the concentration of carbon monoxide gas, the concentration of H2O gas. Now remember, QC and KC are essentially the same thing. We're asked for the equilibrium concentration of the four gases. So the reaction is going to settle, move back and forth, back and forth, back and forth until it reaches a concentration whose formula is equal to 5.1. So let's calculate QC here. Are these really equilibrium concentrations, 0.050 molar for each of these? Well, let's find out. Our QC here is going to be 0.50, equilibrium concentration of this, 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 and that. So we'll just plug that in. Have to worry about units for our equilibrium constant, so I'll just plug in. Do that, we get an equilibrium, a reaction quotient 1, and the reaction quotient Kc, the reaction quotient Qc to the actual equilibrium constant Kc. Do our alligator claw rules, equilibrium constant, the reaction quotient, and we compared the two. We calculated Qc as 1. Well, Qc is 5.1. So C is less than C, so the reaction is shifted. According to alligator jaws, the reaction is shifted product side, or the reaction shifts to the right. Now we can draw our ice table with the reaction shifted towards the right. Let's do that now. We had these concentrations of the gases. We calculated our reaction quotient and found that it shifts to the right towards the product side. So this is going to be minus x, plus x, and plus x. So at equilibrium, we will have 0.050 minus x as the equilibrium concentration of carbon monoxide gas. Our equilibrium concentration of H2O gas will be 0.050 minus x. The equilibrium concentration of carbon dioxide will be 0.050 plus x, which will be the same as the equilibrium concentration of hydrogen gas. So let's plug in our equilibrium concentrations. Our changes are going to be minus x and plus x. It's just minus x because we have 1 mole that's being carried from the left to the right. So our equilibrium concentration is that 700 K. The value of this is 5.1. The O2 and H2 are going to be 0.050 plus x. Be 0.050 plus x. CO2 will be 0.050 plus x. CO was going to be 0.050 minus x, same as the equilibrium of H2O at equilibrium, H2O gas. Solve for x here, which is our change, and then once we solve for x, we can plug that in to get our equilibrium concentrations. So 5.1 is going to equal to 0.050 plus x squared by 0.050 minus x squared. Take the squares and clump it as one big group. Take the squares and clump it as one big group, and when I do that, I'll get 5.1 equals 0.050 plus x divided by 0.050 minus x. That will be whole squared. Take the square root of both sides of the equation. So taking the square root of 5.1 and taking the square root of this pops out the fraction of everything that I need to solve for x. Root of 5.1, 0.258. I'll just carry some extra digits here. That's equal to 0.050 plus x. Let's isolate our x term here. Distribute this. 0.1129, I'll just go 113 to 0.258x 050 plus x. The x is to the other side. I'll move this x here and I'll move that constant there. So I'll get 0.113 minus 0.050 to this moved here plus 1. So x plus 2.258x. This is 3.58x. Solving for x, 0.063 divided by 3.258, 193. It's going to be to change x. The x value is going to be 0.0193, and that's what you want to calculate back in here to get your equilibrium concentrations. So our equilibrium concentration of CO gas is going to equal to the equilibrium concentration of H2O gas, more than 0.050 minus x. reactants we just calculated to be 0.0193. 0.050 minus 0.0193, 0.03, it fakes 0.013 molar. And then my equilibrium concentration of CO2 should equal my equilibrium concentration of H2 gas. Going to equal to 0.050 plus change x. And again, as before, we calculated our change x to be 0.0193. 0.50 plus 0.0193 give 0.0693 molar. Be our equilibrium concentrations. Now we can do a check. Are these truly the equilibrium concentrations? If they truly are, we should be able to plug them back in here and recapitulate the original equilibrium constant. So let's do that check here. Remember, our equilibrium constant 5.1 equals to the concentration of CO2, concentration of H2O by the concentration of CO, concentration of H2 gas. Equilibrium concentration is going, equilibrium expression is going to be our equilibrium constant equaling the products over the reactants, so CO2 concentration times the H2 concentration divided by the CO concentration, H2O concentration, products over reactants. We got our values in, so our equilibrium concentration of CO2 and H2, 0.0693. They're both 0.0693, so I'm going to go 0.0693 squared. Equilibrium concentration of CO and H2O, we calculated that to be 0.31. So it's 0.031, so I'll just put that squared. And does this equal to 5.1? I'll check quickly on my calculator. Get an answer of about 5.00, and what we got was 5.1. I think that's close enough for me to be comfortable in that stating that these are indeed the final concentrations, equilibrium, when this reaction approaches equilibrium.